There is something very special about this video that I can't wait to share. This is my first video after my second COVID vaccine. Peace out, COVID! Woo! All right, back to physics. So, we are going to start now talking about some certain properties of electromagnetic radiation. And by that, I mean properties of light. The first of these properties that we're going to talk about is polarization. Okay? This is very, very different from electric polarization, so get that out of your head right away. And here's what we mean by polarization. This is the thing about polarized sunglasses that make it so much easier to block out light. And what's going on is this. So imagine you have some electromagnetic radiation, right? And imagine that that light is coming at you like this, right? And you have an electromagnetic wave that's traveling towards you. Now, here's the thing. Of course, that light's not just going in one direction, right? It's not jiggling just up and down. You're going to have some that's jiggling this way. And you're going to have some that's jiggling this way. And you're going to have some that's jiggling this way, right? So if you look at these little jiggles as like arrows, right, then you will have light moving towards you at all these different orientations. Jiggling this way, that way, all the different ways, lots of different jiggles, okay? And that is what you would call unpolarized light, right? It's jiggling at all 360 degrees, right? But let's suppose that we cut the rest out and we have it so that light is only jiggling in one direction, all right? This would be polarized light. Right? So if you can find some way to do this with a polarizer, right, then you've cut out all these extra beams, right? You've eliminated all this extra light, and now you have just this light that's in one direction. That's why, like, if you turn the polarized sunglasses, it radically changes whether or not you can actually see the light, right? So this would be unpolarized. Okay. Now, there's a very basic mathematical rule as to how much light a polarizer will cut out depending on what angle the polarizer is at, right? So, when you can see from this drawing here for how a polarizer works, so you have this polarizing sheet, right, that almost has these little gratings that allows light to only move in one direction, right? So you can see that there's like these vertical gratings for this light, this polarizing sheet in this picture, right? And so these little gratings will chop off all the light that's moving on any axis besides this axis, okay? Besides the vertical axis. It only allows that. So you see in this picture that you have this unpolarized light that's both going, jiggling in the y-axis and also jiggling in the x-axis. Then it goes through the polarizer and it's only jiggling in the y-axis, in the direction that the polarizing sheet is designed to cut out the light, all right? And so this is one way to limit the amount of light that reaches your eyes, okay? So there's a question, which is, well, how much light actually reaches your eyes? And so often when we talk about light, we talk about the quantity of intensity, okay? And so intensity is really a measurement of the amount of power, right, per area. So power per meter squared, okay? And so the intensity of light is going to reduce by this equation of, here it is, okay. So if polarized light is already polarized, okay, if the light is already polarized, then it reduces the intensity by a factor of I naught, which is the original intensity of the light, right, times cosine squared theta. Okay? And so you could turn this very easily into a percentage, right? The percentage of the light that's cut away, or that actually remains, is going to be cosine squared theta, right? anytime you have the amount of intensity that you actually have divided by the original, you're talking about a percentage. So that percentage of the light that remains after a polarizer is just equal to this factor of cosine squared theta, where theta is the angle that the polarizer makes with the light, right? So, for example, in this picture here, you can see that the light is polarized vertically, right? So you have perfectly vertically polarized light, right? And then it goes through a polarizer where the axis here is set 15 degrees away from the vertical axis, right? So the question is, what would be the new intensity of the light, okay, if suddenly you put this polarized light through another polarizer that's 15 degrees away from the polarization axis, which in this case is the y-axis, okay? How would you do that? Very, very simple. So your new intensity will be the old intensity times cosine squared of 15 degrees. Simple as that, right? And so cosine squared of 15 degrees is about 0.93. So it'd be 0.93 I naught. If we look at this as a percentage, right? If we look at this instead as I over I naught, we get 0.93, which would be 93%. So in other words, 93% of the original light would still come through if you put polarized light through another polarizer that's 15 degrees off the axis of the original polarization. All right? That's a lot of big words for a very simple concept. If you put polarized light, once again, this equation is only for already polarized light, through another polarizer that's offset by some amount of degrees from the original axis, then the amount of light that remains is cosine squared theta. Okay? So if I were to create a set of sunglasses with a polarizer, then by having this polarizer set off by 15 degrees, I could go ahead and cut off 7% of the light. Not a heck of a lot, but you can design your sunglasses however you want to. Okay? Okay, so that's how it works if you have polarized light. Now, what happens if you put unpolarized light through a polarizer? You can check out the next slide here. So once again, unpolarized light is the light that's jiggling in all 360 degrees. Okay? So let's say you have light that's jiggling this way, right, this way, all the ways, okay? And you put it through a polarizer that's perfectly vertical, right? Then you get a new intensity that's always 1/2 the original intensity. Super, super easy breezy, okay? Let's say that you have unpolarized light, and it's jiggling in all these different directions. It's one time that my drawing skills don't have to be good. And let's say that you put it through another polarizer instead that's this direction, right? Again, you have 1/2 the original intensity. If it starts out as unpolarized light, it doesn't matter which direction, obviously, because this doesn't care about any directions, right? It doesn't matter which direction the polarizer is oriented, you will always get 1/2 of the original intensity back, okay? Now, here's something interesting, right? If you put, and you can go to the next slide here, it says, what is different about the way these two polarizers are oriented? So here's what's interesting, right? If we go from here to here, we're going from unpolarized light through one polarizer, which reduces the intensity by 1/2, and now coming out of here, we have perfectly polarized light. Okay? We're cutting off all the other directions of jiggling except for the one that's totally vertical. Okay? So we get, out of this comes vertical light that's 1/2 the intensity that it was before. Okay? But now what if you take this and put it through another polarizer that is 90 degrees offset from this? Well, we use our old equation. This is now polarized light, so we can use the formula I equals I naught cosine squared theta. But theta in this case is 90 degrees, right? Because the light's polarized this way, but my polarizer is oriented this way. So that's 90 degrees, which of course is 0. So your new intensity will be 0. Okay? What does this tell you? This tells you that if you take unpolarized light and put two polarizers in front of it, one that's oriented 90 degrees, the other one that's, one that's oriented any which way, and the other one's oriented 90 degrees apart from the original one, then you block out all of the light. And you can see it here in this example where the second set of polarizers, the one on the right, cuts out all of the light completely, and you see this perfectly black square, right? But the one on the left, that is actually the case where you have the same orientation of polarizers twice, right? In which case, the light that comes out of this is all pointing in this direction. And so putting it through another polarizer in the same orientation doesn't really change the amount of light that goes through, okay? However, if you put a second polarizer that's perpendicular to the original polarizer, then you cut off all of the light, all right? So you have some kind of a, selection here, a way of actually twisting and turning and cutting off choosing exactly the amount of intensity that you want. And this is, what folks do when they're designing sunglasses that are optimal for our eyes. Okay, so from this, I want to share one misconception question, and it's kind of a fun question. It says, if unpolarized light is incident from the left on 3 polarizers, in which case will some light get through? Okay, now remember, if you have a situation where there is 2 polarizers that are 90 degrees misoriented from each other, back to back, you will lose all light. So we can cut off those for sure. We know that no light will get through those polarizers. What cases have that? Well, I look at case 1 and case 3. In both cases, I see a vertical and a horizontal polarizer oriented directly in front of each other, which will cut off all light. So in cases 1 and 3, no light will come through, so that leaves only the possibility of case 2. Okay? Now, so what about case 2? What's going on there? Okay, so this is really, really interesting, right? For case 2, we have light that's unpolarized, goes through a polarizer that's horizontal. We get horizontal light that comes out of that, right? Polarized horizontal light. But then it goes through a polarizer that's diagonal, right? So what comes out of there is an intensity that's equal to I naught cosine of, this is 45 degrees, right? So that's cosine squared 45 degrees, right? So you're going to have some light coming out at this polarization from this. Cool. So then when you finally do the last one, which is a totally vertical polarization, then you have another one of these equations because that's oriented now 45 degrees relative to this polarizer. So what is fascinating about this is that the order of the polarizers matters. You could take 3 polarizers, right, and just change the way in which they're ordered, and you can go from a situation where no light gets through, in the case where you have a vertical and a horizontal polarizer back to back, okay? Then it doesn't matter whatever you put after this because no light is going to come out of that, right? But if you happen to put this diagonal one in between them, then you can actually get some light because going from here to here, you're not cutting out all the intensity because you're bound to this equation at that point. It's kind of weird. Light's weird. And that's one of the fun and interesting things about it. That's polarization in a nutshell. And when we come back, we're going to talk about another type of quality of electromagnetic radiation, which is called refraction. It's the reason why light bends. It's the reason why when you put a little pencil inside of a glass, or a straw, it looks like it bends like that. And I'll see you there.